Hi everyone. So in the last video, we learned how to graph curves that are defined by parametric equations. And so in this video, we're going to focus on how to use calculus with these types of equations. So specifically, we're going to focus on how to find derivatives, so dy dx, as well as the second derivative. And then also, we're going to use integration to find the arc length of a curve defined by parametric equations. So the first formula I want to tell you about is how you actually find the derivative dy dx. So the formula for finding dy dx is that dy dx is going to be equal to dy dt divided by dx dt. So basically, one thing that I just want to point out here, and we'll see this in an example in a moment, is that when you actually find dy dx for these curves, your answer is going to be in terms of t. So it's not going to be a derivative that's given to you in terms of x or even x and y. It's going to be a function of t. And the reason for that is that you're finding, dy dt is going to be a derivative in terms of t. dx dt is also going to be a derivative in terms of t. And so your expression is just going to have t's in it. So we'll see how that plays out in a moment. So why does this formula work? And actually, let me just add one thing here first. So what is the meaning of dy dx in, an example of a parametric curve like the one I have sketched here? Well, just like with regular functions or regular curves, dy dx just means the slope of the tangent line at various points on the graph. So dy dx is just the slope of the tangent line. And the only difference with, regular kind of situations that you see in calculus is that instead of plugging in the x and y coordinates of the point where you're trying to find the slope, you have to know what the value of t is at that point. And so for the most part, you'll be aware, like the problem will ask you, find, the slope of the tangent line when t is equal to 2 or something like that. But we'll also see an example where we have to figure out what t is, and that's not too hard either. But yeah, so just like normal, dy dx just means the slope of a tangent line. Only difference is that it will be a function of t instead of x or of y. So, why is this formula true? Well, there's a couple ways you can see it. I think the simplest way to see it is to just think of, in a lot of cases, you can think of these derivatives, dy dx, dx dt. In a lot of ways, they behave like fractions, right? I'm just going to copy this and erase some of this stuff, right? So like just, for example, when we're doing like substitution, right? You kind of separate out the du and the dx, right? They kind of act like a fraction. And so similarly here, if you're viewing these as fractions, well, the dt's are going to cancel out, right? If you were to rewrite this as, so when you're dividing a fraction by another fraction, you would have dy dt times dt over dx, right? Because dividing by a fraction is the same as multiplying by the reciprocal. So these dt's would cancel out and you'd be left with dy dx. So personally, that's how I remember this formula. I just think of the t's canceling out. Another way of understanding, why this works is to think about the chain rule. So let's say that you wanted to find the derivative of y with respect to t. So, and let's say that y is a function of x. So if y is a function of x, and then x in turn is a function of t, then by the chain rule, if you were trying to find dy dt, so if you're trying to find dy dt and y is a function of x and then x is a function of t, the chain rule would tell you that you would first need to take dy dx. That's kind of the first part of the chain rule. And then you would need to multiply that by dx dt. Oops. Oh my gosh. There we go. So this is just the chain rule. And so if you take what I just wrote down here and you just go and divide both sides by dx dt, then you'll have exactly the formula that we have written above. So, by the way, all of the formulas we're going to discuss in this video, I'm going to give you on your final as like on a formula sheet, because I know it's a lot of formulas. They're new. You don't have that much time to learn them. So I will be providing these for you on the test. But again, I think the easiest way to remember this derivative is just this first thing I wrote down with the kind of canceling of the dt's. Okay, so let's see an actual example of this. So let's say that we had, so this is one that was actually on your worksheet for the previous video. So this is the curve defined by x of t is equal to t squared plus t, and y of t is equal to t squared minus t. And so we're going to find dy dx. I'm forgetting which color did I use. Let me just try to be consistent here. No, I used blue for dy. Okay. So we're trying to find dy dx. So the first thing we need to do is we need to find dy dt. So how do we find dy dt? Well, it's basically just, that's the same as y prime of t, right? So you just kind of focus on the function that's only a function of y, or y as a function of t, and you take that derivative as you normally would in, Calc 1 class. So dy dt is going to be equal to 2t minus 1, right? So that's what I mean. Just literally take the derivative as you normally would in a calculus class. And then what is dx dt? Well, that's going to be equal to 2t plus 1. And so that tells us that dy dx is just equal to 2t minus 1 over 2t plus 1. And that's it. So in some cases, there will be some simplification you can do with the numerator and denominator. In this case, there isn't. So that's it. You're done. That's the derivative, or that's the slope of the tangent line. And so another thing we could ask here, so maybe I'll say number 1 here, another thing that we could ask is to find the slope of the tangent line when t is equal to 1. So how would we do that? We would just literally plug in 1 for t into our expression for dy dx. So we would say dy dx in this case is equal to 2 times 1 minus 1 over 2 times 1 plus 1. So in the numerator, we would get 1. In the denominator, we would get 3. And so that's our answer. And so if we go and look at the picture, so it's maybe not going to be clear immediately where this tangent line is. So how would we figure out what is the point where this is happening? We would have to plug in t is equal to 1 to find that point. So if we plug in t is equal to 1 into the top equation, we would get 2, right? 1 squared plus 1 is 2. And then the bottom equation, if we plug in 1, we get 1 minus 1, which is 0. And so this is the point. This is the point where t is equal to 1. So when t is equal to 1, we get 2 for x, 0 for y. And so we just figured out that the slope of the tangent line at this point is 1/3, which looks reasonable, right? It looks like it's a positive slope, but it's not very steep. Okay, so that's how finding the first derivative works, and we'll do another couple examples later on in the video, but I also want to tell you how to find the second derivative. So the formula for the second derivative, maybe let me put a box around this because this is important. Actually, it's okay. I can't find a way to put a box around it that doesn't cut things off. It's okay. I'll leave it as is. So that's the first important formula, right? Is that dy dx is dy dt over dx dt. So the next important formula to know is finding the second derivative. So the way that you write down the second derivative is something that I just want to quickly remind you of. So the way that you write down the second derivative in general in this notation is you say d squared y over dx squared. And the reason for that is basically that d dx together, that's the part that means you're taking the derivative. It means like you're taking the derivative of y. And so if you're taking the second derivative, you're not squaring y, you're just kind of doing the derivative part twice. And so this is the part that you're doing twice. So that's why this notation looks the way it does. So how do you take the second derivative? Well, I'm going to write down the formula, and then again, I'll kind of explain where it comes from. So the formula for this is that you're going to take d dt, so the derivative with respect to t, of dy dx. So whatever you got for the first derivative, you're basically taking the derivative of it again with respect to t. And then in the denominator, you do dx dt. So basically the numerator is kind of taking a second derivative, whereas the denominator, you're just putting the derivative of x with respect to t that you found in the earlier part. So this is the second derivative. And what does the second derivative tell you? It tells you about concavity, right? So when you learned in your Calculus 1 class that when the second derivative is positive, your graph is concave up. When the second derivative is negative, your graph is concave down, and it's the same thing here. So the first derivative tells you the slope of the tangent line. The second derivative tells you about concavity. So specifically, when the second derivative is positive, so when d squared y over dx squared is positive, that means your graph is concave up. And when the second derivative is negative, that means that your graph is concave down. Okay, so where does this come from? You know, why is this a thing? Like, why is this how the second derivative works? Well, what does it mean to take the second derivative of this function? So if you have d squared y, so you're taking the second derivative of y with respect to x, another way of writing this would be to say we're taking the derivative with respect to x of dy dx. And that's kind of what I meant about why the square is on the d part, because you're taking the derivative with respect to x of dy dx. So the y part is not getting squared. And so from here we can expand, right? We know how to find, or actually we can expand this d dx part. So what's another way of writing d dx? And let me maybe actually use another color here to emphasize this. So if you have d dx, you can rewrite that as d dt over dx dt. So d dt over dx dt. So why can you rewrite it that way? Well, just think about, again, that thing with fractions, right? The dt's would cancel out here. And so I'm just rewriting that part, and we get this. And then we can just kind of rearrange this a little bit more nicely and rewrite it as d dt of dy dx over dx dt. And that's exactly the formula that I wrote down above. Okay, so let's, I'm going to copy this so that when we do our next example, we can have it on hand. But yeah, let's now find the second derivative for the same example we just did. So third thing we're going to do is we're going to find, now again, d squared y over dx squared. Okay, so we saw that the formula was this. So we already found dy dx earlier, right? So we found dy dx up here. Dy dx was equal to 2t minus 1 over 2t plus 1. And so the first thing we need to do is we need to focus on finding the taking the derivative with respect to t again of this. So this is going to be d dt of what we had before, right? We had 2t plus 1, or sorry, it was 2t minus 1, I think, over 2t plus 1, yeah. So how do we take a derivative of something like this? Well, we actually have to use the quotient rule. So how does the quotient rule work? Well, we take the derivative of the numerator first. So the derivative of the numerator is just 2, and we multiply that with the denominator, which is 2t plus 1. Then we take the derivative of the denominator, which is also 2, and we multiply it with the numerator. And then in the denominator, we take the original denominator and we just square it. So this is going to give us, in the numerator, we have 4t plus 2 minus 4t plus 2. And then in the denominator, we have 4t squared plus 4t plus 1. And so in the numerator, notice that these 4t's are going to cancel each other out. And so we're going to be left with just 4 over 4t squared plus 4t plus 1. So that's going to be our numerator. So we just took the derivative again of what we had already found for dy dx. And then what's the denominator? Well, it's just dx dt. So dx dt, we found earlier, it was this, right? dx dt was 2t plus 1. So we're just going to put 2t plus 1. So we're going to get here, again, we got 4 over 4t squared. And actually, I think it probably would have been better to just leave this as 2t plus 1 squared. So let's leave it like that. And then the denominator, we found that dx dt was just 2t plus 1. So another way to write this would be 4 over 2t plus 1 squared times 1 over 2t plus 1. And so at the end of the day, we get 4 over 2t plus 1 cubed. So some quotient rule will come up in these. You have to remember how to take the derivative with the quotient rule. And then, in some cases, there will be some simplification so that the first derivative does not end up being a quotient. But in some cases, you will have to use the quotient rule. So let's answer one more question about this. So let's find the concavity. So is the curve concave up or concave down? When t is equal to 1. So we already know what that point is on the graph, right? It was the point 2, 0. So how would we figure that out? Well, we would just plug in t is equal to 1 into our second derivative. So if we plug in t is equal to 1, we get, so the second derivative was d squared y over dx squared. We found that the second derivative was 4 over, and so now we'll plug in 1 for t. And so we end up with 4 over, so this is 3, right? 2 plus 1 is 3. 3 cubed is 27. And so this is a positive number. And so our answer is that it's concave up. And we can confirm that looking at our picture. So at the point at 2, 0, this graph is concave up. Remember, concave up looks like, if water were to be, if it was raining, it would collect water, right? It's cupping upward. Whereas this part of the graph here, this part is concave down. So if we had picked an earlier value of t, we would get something that's concave down. But at the second half of the graph here, it's concave up. It's curving upward. Okay, I want to do one more example, or actually we'll do two more, but one more kind of just straightforward example of finding the first and second derivative, just because I think the kind of algebra and simplification will go a little bit differently in this one. So in this example, we have the parametric equations, x of t is equal to sine of t, and y of t is equal to cosecant of t. So this was another one from the previous worksheet. And so, by the way, when you eliminated the parameter on this, you should have gotten y is equal to 1 over x. So why is that? Well, if x is sine of t and y is cosecant of t, cosecant is 1 over sine, right? So 1 over sine is the same as 1 over x. And you can go look at the worksheet from the previous video for like a little bit more detail about that. So there's one difference. If you look at this graph, it doesn't look quite like the graph of 1 over x, right? 1 over x is supposed to continue like this. So why is that? Why doesn't this graph contain these pieces? Well, let's think about what maybe restrictions might exist on these functions. So if x is equal to sine of t, what is the very, very biggest number that sine can ever equal? You know, imagine you're plugging in all different values for t. What's the biggest result that you could ever get for sine of any number? Well, it's 1, right? Sine of something cannot be bigger than 1. And so that's why the graph does not extend this way, right? It ends here because that's the biggest x value you're ever going to get. Sine of any number is never going to be bigger than 1. So this graph does not contain any x values past 1. And similarly, it doesn't contain any x values past -1 because sine also cannot be less than -1. So that's why it looks kind of like 1 over x, but it's like missing some pieces. But yeah, so basically all I want to do for this example is find dy dx and also the second derivative. So first let's find dy dx. Okay, so what is dy dx going to be in this case? Well, we want to start by finding dy dt. So dy dt is going to be the derivative of this second function, right? And so dy dt, what's the derivative of cosecant? So that's one that you might not remember off the top of your head, but it's negative cosecant cotangent. Oops. Oops, t. And then what's the derivative of sine? So that's dx dt. That is equal to cosine of t. And so how do we find dy dx? Well, now we just put these things into a fraction, right? So we say negative cosecant of t times cotangent of t all over cosine of t. And, you know, we could leave it like this and, you know, then we'd have to use the quotient rule and it would be kind of complicated in the next example. So it might be nice to rewrite this in terms of sines and cosines and see if we can cancel anything out. So another way of writing cosecant would be 1 over sine, right? So we have negative 1 over sine of t. And then cotangent can also be written as cosine of t over sine of t. And then if we're dividing by cosine, that's the same thing as multiplying by 1 over cosine. Okay, so let's see how things simplify here. Well, we can get rid of a cosine. And so we're going to be left with negative 1 over sine squared of t. And another way of writing this would be negative cosecant squared of t. So that is our first derivative. And then now let's find the second derivative. So now we're going to find, so d squared y over dx squared. Okay, so how does this formula work? Well, we have to find the second derivative of dy dx, or I guess I should say the first derivative of dy dx. So we'll take another derivative is what I'm trying to say of what we just got in the previous one, and then we divide that by dx dt. Okay, so we want to take the derivative of negative cosecant squared. So this is going to be a slightly annoying derivative, but basically we're going to have to use the chain rule, right? So what's another way of writing negative cosecant squared of t? Well, we can rewrite this as negative cosecant of t squared. And the reason I'm rewriting it that way is because I think that helps with applying the chain rule. So how does the chain rule work? Well, the outer derivative will just bring down this 2, and so we'll get negative 2 times cosecant of t. And then we have to multiply by the derivative of cosecant, which we already saw was negative cosecant cotangent. And so altogether, this gives us 2 cosecant squared of t cotangent of t. And then we already know what dx dt is, right? We found that earlier. Dx dt is just cosine of t. So let's put this all together and see what simplification we can do. So in the numerator, we get 2 cosecant squared of t cotangent of t. Oops, t, not x. And then in the denominator, we have dx dt, which was cosine of t. Okay, so let's rewrite everything in terms of sines and cosines again to help us see what we can simplify. So we're going to get, in the numerator, we'll have 2 over sine squared of t times cosine of t over sine of t. And then if we're dividing by cosine of t, that's the same as multiplying by 1 over cosine of t. And so plays out pretty similarly, right, to the last one. The cosines are going to cancel out. And so we're left with 2 over now sine cubed of t. And so another way to write this would be 2 times cosecant cubed of t. So especially when you're dealing with trig functions, there's just, there's simplification that can happen. So, make sure that you're simplifying fully before you go on to take the next derivative, because I think if you had left your first derivative like this, and you had to then take another derivative of that, that would kind of be a mess. So, be aware that simplification can really make your life easier if you do it before you move on. Okay, there's one more example I want to look at just because I think it brings up something kind of interesting about parametric curves. So the one that we have here is x of t is equal to t squared, and y of t is equal to t cubed minus 3t. So what I want to do here is I want to find the slopes of both tangent lines at the point 3, 0. So both tangent lines, that might sound a little weird. Typically we're used to a graph having only one tangent line at each point on its graph. But let's look at the point 3, 0. So imagine kind of tracing out this graph, right? First we come in this way. And so at this point, we're going to have a tangent line that has a negative slope, right? If I'm just, forget about the other part of the graph, just picture like coming through like this. Right now, this point at 3, 0 has a negative slope if we were to draw a tangent line. But then if I keep tracing the graph, we actually come back and trace over this point again. And this time, it has a positive slope. And so there's actually going to be 2 different tangent lines that we can find at this point. So one of them is going to have a negative slope, and the other one is going to have a positive slope. So how can we figure out, what these different, we can't just use one formula for dy dx and expect to get 2 different answers, right? So what's going on here? Well, I just traced it out and we encountered this point at 2 different times, right? So the first time when we had the negative slope, that happened first. And then I kept going, kept going, kept going. We came back around and we hit it again with now a positive slope. And so that means that the t values for these different slopes are going to be different. And so what we need to do is we need to kind of work backwards to figure out what is t. So we need to figure out what is the t value for this point 3, 0. So how do we do that? Well, we can use our parametric equations here. And so notice that the graph actually goes through a y value of 0 another time. It also goes through 0 here. So I think the easier way to find what t is to focus on this equation. So we know that the x coordinate is always going to be equal to t squared. So if we take the x coordinate here and say 3 is equal to t squared, that will tell us that t is equal to plus or minus square root of 3. And so the negative square root of 3, that's the first, right? Like whenever you're tracing these out, you're starting with your smaller t values. And so, imagine if you're plotting the points, you would first plot t is equal to negative square root of 3, right? So that's going to be the one that's going to give us the orange tangent line. And then as we continue, we'll eventually come back again at positive square root of 3 as our time, and that's going to give us the green one. So this one is going to be the negative, and this one's going to be the positive. But you don't even really need to know that. We can just kind of see what we get for both of them, and then that will tell us which one is which. So for the first one, so let's start with the negative square root of 3. So for that one, we'd have dy dx is equal to, so we want to find our dy dt and our dx dt, right? So dy dt in this case is going to be 3t squared minus 3. So our numerator is going to be 3t squared minus 3. And our denominator is going to be dx dt, which is just 2t. So that's our general formula, but now we want to plug in actually negative square root of 3, right, for t. So this is going to give us 3 times negative square root of 3 squared minus 3 over 2 times negative square root of 3. So we're going to get 3 times 3, so that's 9, minus 3, over negative 2 root 3. And so that's going to give us 6 over negative 2 root 3, which can also be written as 3 over negative root 3. Or maybe a nicer way to write it would just be negative 3 over root 3. Hopefully I'm not off screen. Let me scooch over a little bit. So this is our answer for the negative slope, right? This has a negative slope because it's a negative number. And so that fits with this orange piece. And so how would we now find the other one? Well, we would just plug in now positive square root of 3. So if we do dy dx now for the positive square root of 3, we would get 3 times square root of 3 squared minus 3 over 2 times the positive square root of 3. And so this would give us, again, 9 minus 3, but now over positive 2 root 3. So 6 over 2 root 3, and this would end up giving us positive 3 over root 3. And so we can see that we get 2 different slopes of tangent lines at the same x value, but they're at different t values. So that's, again, really, that kind of explains why it's important that dy dx in these is not in terms of x, it's in terms of t. Because it's possible, because these are not functions necessarily, it's possible to have a graph where there's multiple tangent lines at a particular x value or at a particular y value. But there's always going to be, if there are multiple tangent lines, they'll be at different t values. And so by knowing what that t value is and plugging that into the derivative, that will really let you see what's going on. Okay, so that's it for derivatives. And like I said, I'll give you these formulas on the test. It's really just knowing how to apply them, just knowing how to kind of do all the math of this, but it's really, just calculus 1 stuff, taking derivatives. So there's one other topic that we're going to talk about, which is one way of using integration. So we're going to learn how to find arc length. So we'll see that this formula is actually really similar to the one that we already learned, but it's actually even a little bit nicer in some ways. So we already know that, and actually let me first write the formula, and then I'll kind of show you where it comes from. So basically, if you're looking for the length of the arc of the curve defined by parametric equations, x is equal to some function of t and y is equal to some other function of t, from t is equal to alpha to t is equal to beta. So these are just Greek letters, alpha and beta. If you wanted to, you could use a and b. I think they just use these to kind of distinguish that these are not x values, they're t values. So what is the formula? The formula says that you take the integral from alpha to beta of the square root of dy dt squared plus dx dt squared dt. And so there's one important thing to bring up, which is that in order for this to work, you need to make sure that the curve you're looking at is only traversed once from alpha to beta. So I'm going to write that down, and then we'll see an example where that comes out, because I think it's maybe a little hard to understand what I mean by that until we see an example. But this formula is only accurate if the curve is traversed once from t is equal to alpha to t is equal to beta. Okay, I want to show you just briefly before we get into an example, and again, I'll explain where this kind of warning comes from. But I first just want to quickly show you a proof of this, because it's really quick. It basically just comes from the other arc length formula we have, right? So we know that the formula for an arc length, if you have, let's say, it could be y as a function of x, it could be x as a function of y. Let's assume that we have y as a function of x. So we saw that the normal arc length formula would be the integral from a to b of the square root of 1 plus dy dx squared dx. This gives the length of the arc of y as a function of x from x is equal to a to x is equal to b. So let's say, and actually I'm just going to use the letter h here just so that I can use f and g for something else. So let's say that now we know that y is equal to h of x can actually be expressed in the form as well. X can be written as a function of t, and y can be written also as a function of t, right? So we've already seen examples like this, right? Where if you can eliminate the parameter, maybe you can write it as, a function of y or as a function of x, but then you can also have it written in this parametric form. So let's say that you are now kind of rearranging it, rewriting it into its parametric form. So if the curve can be written in parametric form, well, that means that dy dx can also be written differently, right? So let me actually add in my color coding here, because I think it will maybe help us see where some of these pieces come from. So we also know that dy dx, we know that that can be written as I flipped the colors. Oops. So we know that dy dx can also be written as dy dt over dx dt. So let's just go ahead and replace dy dt, or replace dy dx with dy dt over dx dt, and then let's also replace the bounds with alpha and beta, because we're basically going to convert this into parametric form. And then another thing that we're going to change is that dx, well, just based on kind of the stuff that we've been saying with kind of treating these things as fractions, dx can also be written as dx dt times dt, right? Just sort of thinking of treating these as fractions. So let's see what this looks like when we make all of those changes. So again, I guess I'll also just write one thing here. We're going to change this to alpha and beta. So we're just doing all these little tweaks to put it into parametric. So this is going to be alpha and beta. We're still going to have the square root of 1 plus, but now we're going to have this kind of bigger thing here. So we're going to have dy dt divided by, I should have made this bigger. So we have dy dt over dx dt squared. And then I'm replacing dx with dx dt times dt. And let me actually make this purple too, so that we can see how things kind of cancel out. Okay, so the next thing that I'm going to do is I'm going to take this dx dt and I'm going to rewrite it as dx dt squared and bring it inside of the square root, right? You're allowed to do that. It's like, for example, if you have 2 root 3, that's the same thing as rewriting this as the square root of 4 times 3. Right? You can take something outside of a square root, square it, and then bring it inside the square root. So if we do this here, we'll get the integral from alpha to beta of the square root of 1 plus all this stuff and now we're going to be multiplying this whole thing, so both of these things, by dx dt squared. And so we have the dt on the outside. So what happens when we go and multiply both of these things by dx dt squared? Well, we're going to end up with, for the first part, so we're multiplying to this and to this, right? Those are the two things that are getting multiplied with dx dt squared. And so the one part is just going to become dx dt squared. And what's going to happen with the second part? Well, the denominator, right, if you have dy dt over dx dt, that whole thing squared, that means that the denominator is getting squared specifically, right? And so if we multiply by that same denominator squared, then it will cancel out. And so we'll be left with just dy dt squared dt. And this is exactly the formula that I said we were going to get, right? This is the formula that we wrote down, and maybe I'll even add in this color because I just kind of like it. So that's our formula. So it basically comes exactly from the formula that we already learned. It's just kind of a rewording of it for these situations with parametric equations. So I want to just do one basic example, and there will be a few more examples or maybe a couple more examples on your worksheet. But let's say we wanted to find the circumference of a circle. Let's see how this would work to find the circumference of a circle. Or I say specifically, let's say the unit circle. So first we need to figure out, what are our parametric equations and what are the bounds, right? What are alpha and beta? And so we've seen that we can write the unit circle as x of t is equal to cosine of t, and y of t is equal to sine of t for t being between 0 and 2 pi. So let's see how that looks if we put that into the the formula. So our bounds are going to be 0 and 2 pi. And then we have the square root of, okay, so what is the derivative of cosine? So dx dt is going to be negative sine, right? So we have negative sine of t squared. So we're always taking the derivative of each part and squaring it. And then what's the second part? Well, the derivative of sine is cosine. So we have cosine of t squared. So this is going to be the integral from 0 to 2 pi of the square root of sine squared of t plus cosine squared of t dt. And so this will give us the integral from 0 to 2 pi of, well, what's sine squared plus cosine squared? That's just 1, right? And so we have the square root of 1, which is just 1. And so that means that our antiderivative is just t, and we're just evaluating at 2 pi and at 0. And so we get 2 pi as our answer, which that's correct, right? That's the circumference of the unit circle. And you might remember I gave you a question, I think it was on one of your worksheets for like the regular arc length stuff. And you also had to do this process. You had to find the circumference of a circle. It was a lot harder. So I just want to point out that arc length works out really nicely in a lot of cases with this formula. It's just kind of a nicer formula than the one for function. So that's really the reason I wanted to show it to you. So one thing I just want to point out is, we saw in the last video that we have another parametrization for the unit circle, right? So let's say that instead we had used the equations x of t is equal to cosine of 2 times t, and y of t is equal to sine of 2 times t. And let's say we used the same bounds. Okay, so what would happen in this case? Well, now the derivatives of each of these would be a little different, right? So what would the derivative be for the first one? It would actually be negative 2 times sine of t because of the chain rule. So we'd have negative 2 times sine of t plus 2, squared, plus 2 times cosine of, and sorry, I forgot the 2t, my bad. Negative 2 sine of 2t squared plus 2 times cosine of 2t, right? Those are the derivatives of these two equations written above. And so what would be the problem? Well, when we go and simplify this, we would end up with not just sine of 2t plus cosine of 2t, we'd end up with 4 times sine squared of 2t plus cosine squared of 2t. So I'm kind of skipping a step here, but hopefully you all see where this comes from. I just factored out the 4 from both of them, because if you were to take these and square them, you would end up with a 4 on both. And so this would end up being the integral from 0 to 2 pi of not just, in the last time we just had 1 inside the square root. This time, this part is equal to 1, but we still have a 4. And so we would take the square root of 4 and we'd get 2. And so our antiderivative would be 2t evaluated at 2 pi and at 0. And so we would get 4 pi. And that's not right? That's not the circumference of the unit circle. So why is that answer wrong? Well, it's because, remember, if you think back to the last video, if you use this parametrization here with these values for t, this is actually going to traverse the unit circle twice. So this, using these bounds, we actually traverse the unit circle twice. So basically, if you remember in the last video, we talked about this being kind of like a faster parametrization. It moves through the unit circle more quickly. And so the problem is that, why did this come out wrong? Well, it came out wrong because we chose bounds that did not go around the curve only once. So this would be basically twice the circumference. of the unit circle. So how could we fix this? Like if you really wanted to use this parametrization for some reason, because this is a fine parametrization, there's nothing wrong with using this parametrization here. The issue is the bounds. So what would you need to do in order to make this give you the correct answer? You would need to change this to being just from 0 to pi, because then you would only traverse the unit circle once and that would give you the correct answer. So if you were to imagine going through the same process but changing the bounds from 0 to pi, well then you would still get 2 pi as your answer, and so it would be correct. So again, you just have to make sure, and I don't really think this is going to come up, but yeah, you just need to make sure that whatever bounds you're using, that your graph is really only going between those, as you go between those bounds, it's not kind of repeating itself and getting a multiple copy of the part of the graph you're looking at. So as I said, like this formula as well, I'll give this to you on the test. I know I don't want you to feel like you have to memorize a bunch of new formulas now, but yeah, we have the first derivative, second derivative, and arc length. All three of those I'll give you as formulas on your final, so you can just focus on making sure you know how to actually apply them. So yeah, so next video will be about kind of similar taste to the last video and this one, but now using polar coordinates instead of parametric equations. So we'll first learn about, how polar coordinates work. That's something that you should have learned about in your pre-calculus class, but we'll do a review of polar coordinates, and then we'll see how like calculus works in that context as well. So I'll see you then.